Hey folks, this is Major Jones here to talk to you about how the LC3 handles trap instructions, interrupts, and exceptions. And this is the last big piece of the control unit, and the last big piece of the actual sort of data path. You can kind of see here that we update our block diagram just a little bit in order to implement the full LC3. So traps, of course, are the instructions that the user programs call to request services from the operating system. Interrupts are the things that the peripheral devices, like the keyboard, can use to sort of alert the LC3 to the fact that something needs to happen outside of the normal flow of execution. And exceptions is a kind of a general term for things that go wrong in the processor, and which don't have like an immediately, like a nice solution. And so we've kind of alluded to these already, but in the LC3 there are three such exceptions that we need to account for. One is the ACV, access control violation. So this is, we need to plan for what happens if by some horrible sequence of events, the LC3 is thinking it's being instructed to access a part of privileged memory while the privilege mode is still sort of in user mode. We're familiar from the start with the fact that the LC3 does not have an instruction associated with opcode 13. And it's only now that we're sort of identifying this is an exception, right? The LC3 retrieves an instruction from memory and it deciphers that opcode as 13. It knows there's something really wrong. And then the last exception that we need to handle is what's called a privilege mode exception. This is if we are trying to execute the return from interrupt instruction while still in user space. That's kind of a no-go, right? That means something's wrong, something got screwed up, and we need to sort of deal with it. So there are these kind of 6 things, right? Five things. Traps, interrupts, 3 exceptions that we have to deal with. And the book shows us, to start with in section C7. This is actually figure C7, this block diagram right here, how we handle that. So you can see up top here, these are the same 4 phases that comprise my fetch state, and I have highlighted in pink here kind of the different things we have to concern ourselves with. So down here we have, what do we do when we decode the instruction? It's a trapped instruction. We have to worry about, okay, what if in this very first state we test for the interrupt and it's a yes, it's a 1, so we have to handle this interrupt down here. And then you can also see in pink our three sort of down here are 3 sort of exceptions, right? If we decode and we see opcode 13, okay, that's an illegal opcode. We have to do something different. If we at multiple places are accessing memory and there's a mismatch between the fact that we're trying to access privileged memory, but we don't have the privileged mode, correctly. I think it's cleared if we're privileged, then we have to handle that access control violation. And then additionally, we have to worry about, okay, if we're executing the return from interrupt instruction, but we happen to be in user mode, okay, well then there's a privilege mode violation here. All right. So the rest of this lesson, we're going to look at kind of what this state diagram is telling us, and also what that means, how we need to sort of update our little LC3. You can see the changes here in pink that kind of, are the additions we need to make in order to be able to implement this state diagram. Okay, so to start with, I'm going to go back to actually, let's see, I think it's unit 3 is what I want. We'll do operating system routines. Okay, oops. So this is going back to operating system routines. You recall that, the way this is processed is actually very similar to, or almost identical to how the interrupts are processed, right? If we encounter a trap instruction or we get an interrupt, we have to do a couple of things. If we're in user space, we have to, save the user stack pointer and load the supervisor stack pointer into R6. In both cases, regardless of whether this happens in user space or system space, we have to push the current value of the processor status register, PSR, and our program counter, PC, in order to sort of effectively save the state of the LC3. And then we can proceed to either, put ourselves into supervisor mode, get the value we need, and sort of branch to where we're going. Okay, so if I go back to this diagram here, what I want you to see is that number 1, of course, my interrupt, handling my interrupt kind of takes me to this sequence, right? these two states, though, take a look at this is state 45 and this is state 37. You'll notice that if I'm handling an illegal opcode, I also sort of eventually transition to state 37 or 45. If I'm handling the trap instruction, eventually I go to state 37 or 45. If there's a privilege mode exception, I go to 45. If there's an ACV, an access control violation, I go to 45. Okay, so ultimately, all these sort of the trap instruction, the interrupt, the exceptions, they're ultimately, they have some sort of initial stuff that they're doing that's kind of unique, but then they all fall into this sequence right here. And this sequence is the thing we just looked at on the previous slide from Unit 3. I'm pushing here, I'm sort of pushing the PSR onto the supervisor stack. Here I'm pushing the program counter onto the supervisor stack. In these last three, I'm getting the address of where I need to go in order to handle, whatever is happening. And then, I load the program counter with that value, and then I go back to state 18, which is the very first state up here, to start executing that instruction. Okay, so there's a lot of detail here, but this is a very familiar framework, hopefully, to us. Okay, you'll notice also kind of the other big chunk of this state diagram is when I'm returning from interrupt. You can see that. This is the same sequence in reverse, right? I'm loading the memory address register with the stack pointer, which, this one is hopefully the supervisor stack pointer. And I'm taking that value, putting it in the program counter. So this is me popping the last value off the stack into the program counter. Here I'm doing the same thing. I'm loading the PSR, so I'm popping the PSR, and then eventually I'm returning to state 18. Okay, so this is just kind of the same process in reverse. That's kind of the layout of this diagram right here. All right. So we'll take a look at let's do the interrupts. So if there's an interrupt, you'll notice that in this first state here, we do a couple of things, right? Number one, table and vector get set, and table and vector are the two values that sort of point to the correct spot in one of the two vector tables. So it could be the trap vector table, it could be the interrupt vector table. Here, table gets set to 1. You might recall from, let's see, this one. You might remember from our discussion of the memory space that if the value starts at 0, 1, then I'm in my my interrupt vector table. So that kind of matches my intuition. I'm going to set the table to 0, 1. Which vector, sort of which specific interrupt service routine I'm getting is dependent on which was the interrupt triggered. We'll take a look at this later. And then, in addition to sort of getting that, I need to update the priority. I'm going to start pushing the processor status register onto the stack. So I'm going to load that into the memory data register. And then, whether or not I go to state 45 or state 37 depends on whether I was in user mode or supervisor mode. If I was in user mode, and you can see here what I need to do is save that stack pointer. I need to switch those around, right? I need to sort of save the user stack pointer, load the supervisor stack pointer. And so that's what this state's doing. There's a slight typo in the book, so I changed that here. So state 45 should say that we take the stack pointer and save it into the USB, saved USB. And we take our saved supervisor stack pointer and load that back into the stack pointer R6. And then proceed with pushing the PSR, pushing the program counter, and then branching to our interrupt service routine. All right. There is kind of one other slight weirdness in this. I'll say it's two little weirdnesses in the state diagram here. One is that here in state 43, when I'm trying to push the program counter. Before I store it to the memory data register, before I push it onto the stack, I'm subtracting 1 from it, which is a little odd. The reason is because that if I've gotten to this point, I've already executed this first step of the fetch cycle. I don't sort of get anywhere in here without at least executing this first step, which increments the program counter. So the program counter was incremented, sort of assuming that whatever instruction we fetch here in this first few series of states is completed, is actually executed. But the whole reason I'm here in state 43 is because something's gone wrong. Either there was an interrupt or I guess not necessarily wrong, but there was an interrupt or some kind of exception, or, I was processing the RTI and there was a privilege mode or something like that. And so in order for the LC3 to be able to come back to executing, whatever instruction was happening before we got here, it needs to subtract 1 from the program counter, because this is incrementing, assuming that instruction completed successfully, and it's not going to complete successfully if we're here, right? So we subtract 1 to get the correct value of the program counter, and then we proceed. So that's one kind of weirdness. The other kind of weirdness is down here for my access control violations state. You'll notice that there are actually 5 separate state values, all associated with the same state. So if you see, I think it's on the other state diagram really is where we see these, or you can see here, I'm testing the ACV bit, and if there's an access control violation, I go to state 60. So that's down here. Well, there's a couple other places in our state diagram where, if there's an access control violation, we go to state 48 or state 56. And that's just a weirdness based on, the sequencer in our control unit. There's a relationship between, based on kind of how these AND gates and OR gates are set up. There's a relationship between what the next state should be if there isn't an access control violation, and what it should be if there is. And what that means is that for several states there need to be we need to have several different values that each correspond to the same state, the same ACV. Okay, so this is there'll be 5 state numbers that are effectively mapped to the exact same state is all that's going on here. All right. Okay, so let's take a look at the block diagram here, and I'll try to again kind of break this down for you a little bit at a time. So you can see kind of I'm going to break this into 3 groups, right? So I've got a group down here that's sort of below the processor bus. I got one group up here up to the right, which is to the right of my ALU above the processor bus. And one big group here to the left of the ALU above the processor bus. And so what I want you to see from this big group here on the left, really all this logic is doing is allowing us to be able to manipulate the processor status register. So be able to put that sort of on the processor bus or load it with different values. Here we're loading bit 15. Here we're loading the bits 10 to 8. Okay, so basically all we're doing here is, you can see here, like for the privilege bit, right? I've got, a multiplexer that chooses whether or not it's, sort of getting, its same value or new value. And I've also got a little gate now that lets me sort of put that onto the processor bus potentially. So bit 15, I got my priority bit here, same deal, right? I can, update it, or it gets a value from the processor bus, and it also is allowed to put its value on the processor bus. Same here for the condition codes. You can also kind of see actually a little bit of our interrupt software as well. Interrupt hardware. So here's my little comparator that tests whether an interrupt that is requesting servicing has a higher priority than what's currently being run. So this whole kind of chunk to the left is just to allow us to sort of read and write from the processor status register. This little chunk here on the right next to the ALU, this is just us basically here to be able to manipulate the stack pointer. So you can see here, this is actually what's known as a stack pointer mux, and it has a couple of inputs. I've got my saved user stack pointer, my saved supervisor stack pointer. I've got an incrementer, a decrementer, because there's a couple of places on this diagram here where I want to update the stack pointer with itself +1 or itself -1, or I want to update the stack pointer. I want it with a saved value, or put the stack pointer in a saved value. Okay, so this is all just us manipulating the stack pointer. You know what? I almost forgot here. Also, one part of our diagram here is the decrementer for the program counter. Again, remember that's the weirdness here from state 43 when I need to sort of subtract 1 from the program counter. Okay, this little chunk underneath the processor bus is the one that's a little bit more complicated, but it is the whole purpose of this little chunk down here is just to be able to sort of correctly calculate this address table vector. It's to hopefully correctly find the address of the trap service routine or the interrupt service routine that we're about to execute. And so you can kind of see here, I've got 2 parts of this, right? Tables, the kind of that upper 8 bits that picks whether it's the trap vector table or the interrupt vector table that we're looking into. Vector is sort of the lower 8 bits that selects the correct, service routine from inside that table. So table mux appears a couple of places that basically determines, which am I in, trap or interrupt vector table. And then the vector portion, has a couple inputs. One is potentially coming from the lower 8 bits of the processor bus, right? This would be the case if we were selecting or if we were trying to execute a trap service routine. The trap instruction encodes the actual place in memory where I'm looking. I'm going to find the address of my trap service routine that would get 0 extended and sent through here onto the processor bus, and ultimately it would come down here and become this little vector piece. If I'm not executing a trap routine, then I'm executing some sort of interrupt or exception. And so then in that case, the lower bits come from this little multiplexer down here. Int V, remember we looked earlier at int V was sort of a catch-all for, any one of multiple interrupt service routines. That's one option that goes into this lower 8 bits. At the moment, there's really just one interrupt service routine that we can implement. That's for the keyboard, but potentially this would be, coming from, from any of our interrupt service routines. Is it here? I think. Yeah. So recall from our, that potentially if, we have more interrupt service routines, those would, be, populated here. We have more peripherals that have, the ability to raise interrupts and, some sort of memory that's, registering what that interrupt vector is. So potentially lots that are coming from this here. And then I got specific vectors associated with each of my exceptions: privilege mode exception, illegal operation exception, and my access control violation exception. And these values, you might notice, match the control signals for my vector mux. So here, if it's 0, I'm choosing my interrupt vector. Otherwise, I've got a privilege mode exception, opcode exception, ACV exception. It's kind of interesting to note also, let's see if I can pull it up, that if you, oops. Hey folks, this is Captain Jones. Ah, shoot! That's a video that I didn't want to play. Okay, so if I pull up my my simulator here, and let's see if I can find a good one to. Oh, no, I don't want that. Let's do this one. It's just a basic. This is our multiplication program. Okay, so I'm going to assemble that. I'm going to go here. You'll notice if I go to memory location 0100. Okay, this is showing me. This is the start of my interrupt or exception vector table. You notice that 0100 has a value for my privilege mode exception, for my legal opcode exception, for my ACV exception. And so these were called the starting addresses of each of these exception routines. And so if I go to 03B3, then you'll notice that I've got a little program here that runs if I've got a privilege mode exception. It's going to load a message into R0. It's going to put that on the screen, and it's going to automatically halt the processor. So, we didn't have to write this. It's kind of cool that it's in the simulator, but, that would show that kind of what happens when when the LC3 is, when it pulls this address together in the data path, right? If there's a privilege mode exception, we get 0100, and in the simulator we can see that that's actually associated with a little exception routine. All right. Okay. So that's all I got for this lesson here on handling trap, interrupt, and exceptions. The important parts are for you to be familiar with this state diagram. So, again, kind of like before with the control unit, what each state means, what the control signals are within each state, kind of what the purpose of each one is doing. And that, you can see that on this diagram here. You can map, okay, I know that, in state 37, when I'm sending the stack pointer -1 to the stack pointer in the memory address register because I'm about to push the PSR. Okay, what that means is that, what I need R6 to come out here R6 is my stack pointer, right? I need to subtract 1 from it, and I need to send that back into R6, and that's also going to go here into the memory address register to prepare pushing that. So we can kind of understand how the state diagram is implemented using the hardware. All right, folks. That's all I got. See you next time.